Hello everybody, we're going to be doing another momentum problem and we're going to be tackling an elastic collision. Now before I begin, there's just two things that I want to address. The first thing is that I want to apologize for any background noise that you may hear because of the ongoing coronavirus pandemic and the quarantine that's in effect. I don't have access to my usual office. But in any event, I hope that everybody's okay. I hope that everybody is practicing regular hygiene, washing their hands, staying home, and everything that they've been advised to do. But moving forward, the second thing that I want to address is about the elastic collision. I also put this formula here because when you hear elastic collision, in my last video I talked about a perfectly elastic collision. Now those are not the same thing. Okay? In a perfectly elastic collision, kinetic energy is conserved. In an elastic collision, kinetic energy does not have to be conserved. Every perfectly elastic collision is of course an elastic collision, but not every elastic collision is a perfectly inelastic collision. So a perfectly elastic collision. So when you see this and you see elastic collision, please read the question, unless it's explicitly stated that it's a perfectly elastic collision. Please do not use that because that's going to run you into a lot of problems. So looking at this problem, we have a 144 gram baseball moving at 28 meters per second, and it strikes a stationary brick which has a mass of 5.25 kilograms. And it's on small rollers, so it moves without friction. After hitting the brick, the baseball bounces straight back and the brick moves forward at 1.1 meters per second. What is the baseball speed after collision and the change in kinetic energy? So, and that's my bad, I've mislabeled this. So we know the baseball is moving at 28 meters per second initially, and this is stationary, so it's at rest. They collide, the baseball bounces off, and the brick moves forward at this speed. So I've already written everything out on the side, and I've done a bit of quick math, and I've converted the grams to kilograms. Here we have the baseball's variables denoted by B, and we have the brick's variables denoted by BR. So I have the mass, which is 0.144 kilograms, the initial velocity, which is 28 meters per second. We don't know its final velocity, but we're going to find that out. Here I have the mass of the brick, which is 5.25 kilograms. Here I have the velocity of the brick, which is initially 0. And here I have the final velocity of the brick. So let's go ahead and we're going to go straight into conservation of momentum because we know that that holds in all situations. Well, in many situations, a whole lot of situations it holds true. So here I have change, here, change in momentum, initial is equal to change in momentum final, and my initial momentum for my brick is 0. So I'm not going to include that because it's 0. Because so the initial momentum in this system is just the momentum of the baseball. So here, mass of the baseball times final velocity of the baseball plus mass of the brick times final velocity of the brick. So here, this is my target variable, so with a bit of algebra, I'm going to subtract mass of the brick, final velocity of the brick from both sides. And that's going to leave me with mass of the baseball times final velocity of the baseball. Now, this is something that I can solve for because these are all things that I know. I'm going to divide both sides by mass of the brick. And before you go dividing, you have to make sure that what you're dividing by is not 0. Luckily, in our case, we don't deal with 0 masses. So I end up with velocity of the baseball final, which is mass of the baseball, initial velocity of the baseball, mass of the brick, final velocity of the brick, all divided by this term here. And again, I like not to plug numbers until the end because something may cancel and make the calculation easier for me. So in this case, these two cancel, but these two do not cancel. You can't cancel something off this term here and then cancel this term because these two have to be the same, okay? So this leaves me with initial velocity of the baseball minus mass of the brick, final velocity of the brick, divided by mass of the baseball. So this becomes 28. This is 28 minus mass of the brick, which is 5.25. 5.25. I'm going to put these brackets here. Okay, this is velocity of the brick, final velocity of the brick, which is 1.1. Divided by mass of the baseball, which is 0.144. Now I'm going to compute this first. So we have 5.25 times 1.1. Which is, and now I'm going to divide this by 0.144. So I end up with 28 minus 40.0. For consistency, I'm going to cut that down 2 decimal places just to reduce the error. In general, you shouldn't add two numbers with a different amount of decimal places because one number you know more accurately than the other number. So 28 minus 40.1. And this gives me negative 12.1 meters per second. And this makes sense because when the baseball collides with the brick moves forward and the baseball bounces back. So the baseball recoils with a speed of negative 12.1 meters per second. And going back to this perfectly inelastic collision formula, what this says is that the difference between the final velocity and the two initial velocities should be equal to the difference of the final velocities. So we know that VB, initial velocity of the other object, is 0. So here, this is going to be 28. And if I were to go here, this number, this final velocity right here, this is 1.1. And right here, this is what I'm looking for. This is the velocity. This is the final velocity of the first object, which is the baseball. So this is negative 12.1. So if I were to put that in there, this would be 28 is equal to 13.1, which is completely ludicrous. So I just did that to show you why that's not true in this particular case, and that you'd only use that when instructed.